Hey there, and welcome. Have you ever really looked at a simple drop of black ink and wondered what's actually in there? We're surrounded by mixtures every single day, right? From the air we breathe to the coffee we drink. But how do scientists unmix them to see what they're truly made of? Well, today we're going to dive into the really cool and powerful technique that does exactly that.
So here's our game plan. We'll start by cackling that ink mystery. Then we'll get into what I like to call the great chemical race. That's the secret to how this all works. We'll check out the forces of attraction that are basically the rules of the race, see it happen live with paper chromatography, and then we'll reveal the incredible invisible world this technique opens up. Okay, so let's start with a little puzzle. You see that simple black dot from a marker pen? It looks pretty boring, pretty straightforward, right? But what if I told you it's not one color at all? What if it's a secret cocktail, a carefully crafted mixture of different colored dyes? How in the world could we prove that? Well, the tool for the job has a fancy name, chromatography. But don't let the name scare you. At its core, it's just a physical way to separate all the different parts of a mixture. You can think of it like a microscopic sorting machine for molecules. And this is exactly how we're going to crack our ink mystery wide open. All right, our mission is officially a go. We are going to unmix that ink. The question is, how? We do it by setting up what I'm calling the great chemical race. Now, to get your head around chromatography, I want you to picture a race. But instead of runners, we've got molecules. Every mixture, like our ink, is a whole team of different racers, and our goal is to get them to finish at different times. That way, we can see each one all on its own. You know, every race needs a track, and this one has two crucial parts. First, there's the terrain, or what scientists call the stationary phase. This is just the stuff the racers have to move across. It could be a solid, like a piece of paper, or even a liquid. Then, you've got the current, or the mobile phase. This is what pushes the races along. It's a solvent, maybe a liquid or a gas, that flows over the terrain, carrying our little molecules with it. So here's the key idea. Not all racers move at the same speed. It's just not going to happen. Some are going to be super fast, and others are going to be slow. This whole process of separating them based on their different speeds is the absolute core of chromatography. It's called differential migration. Yeah, it's a fancy term, but it really just means the molecules migrate, or move, at different rates. Simple as that. So why do we go to all this trouble? Why run this race in the first place? Well, it lets us do three incredibly useful things. One, obviously, is to separate stuff, just like we're about to do with our ink. Two, it helps us identify what those separated things actually are. And three, we can figure out exactly how much of each substance was in the original mix. Pretty powerful stuff. But that leaves a big question, right? What makes some of these molecular racers fast and others slow? Well, the answer is all in the rules of the race, which comes down to the forces of attraction between the molecules. So what is it? What's really slowing some molecules down while others just zoom on by? The answer actually lies in a fundamental property that every single molecule has. And that property is called polarity. Probably the easiest way to think about polarity is as a molecule's natural stickiness. That's it. Some molecules are just inherently stickier than others, and that stickiness is what's going to determine how they do in our race. So where does this stickiness even come from? Well, it's not actual glue, of course. It's a combination of all these little weak attractions between molecules. Now, this diagram shows some of the physics, things like hydrogen bonds, that cause molecules to cling to surfaces. But listen, you don't need to be a physicist to get the main idea here. So here is the absolute golden rule of the race. Like attracts like. It's that simple. If our terrain, the stationary phase, is polar, or sticky, then the stickiest, most polar molecules in our mixture are going to grab onto it and hold on tight. And that slows them way down. Meanwhile, the less sticky, non-polar molecules, they're not as attracted, so they get swept right along by the mobile phase and travel much, much faster. Okay, enough with the theory, right? Let's actually see how this all comes together, and we're going to use one of the simplest, most visual forms out there, paper chromatography. This is exactly how we're going to solve our ink mystery. You know, the process is actually wonderfully simple. You start by putting just a tiny spot of your ink on a special piece of paper. That paper, that's our polar, sticky, stationary phase. Then you just dip the edge of that paper into a solvent. That's our mobile phase. The solvent starts to creep up the paper, and as soon as it hits that ink spot, The race is on. The different colored dyes in the ink start traveling up the paper, but all at different speeds, separating out beautifully as they go.
And this is what you get. This is called a chromatogram. You can see it clear as day. Our original black spot has split into different colors. The ones that traveled the furthest, those were the least sticky, and they were happier to be carried by the solvent. The ones that barely moved from the starting line were the stickiest ones, the ones most attracted to the paper itself. Now, to make this all very scientific, we can calculate something for each spot called the RF value, which stands for retardation factor. Basically, by measuring how far a colored spot traveled compared to how far the solvent front traveled, we get this unique ratio. And here's the cool part. Under the exact same conditions, this value is like a chemical fingerprint, unique to that specific compound. But what if you have a really complex mixture and all the spots are still kind of overlapping? Well, you can run the race in 2 dimensions. You just run the chromatograph once, let the paper dry, turn it 90 degrees, and then run it again in a completely different solvent. This spreads all the spots out over the whole sheet, giving you this incredibly detailed separation. So there you have it. Mystery of the ink solved. But this whole chemical race idea is used for so much more than just separating colors in a marker. It is a key that unlocks the invisible world that's all around us.
You know, the basic principle of this race is just so versatile. Scientists have gotten really creative and designed all sorts of different tracks. They use thin layers of silica on glass, they pack long columns with special material, and they even use gas to carry the racers through these high-tech ovens. The list goes on and on. So where does this all matter in the real world? Well, think about this. When an Olympic athlete gets tested for performance-enhancing drugs, the technicians are using a super sophisticated form of chromatography to find and identify even the tiniest trace of a banned substance. It is also absolutely crucial for our safety. Chromatography is used all the time to test our food for nasty stuff like pesticides or even to find undeclared allergens. It separates out all the components in a food sample to make sure what we're about to eat is actually safe. And for all you crime show fans out there, in forensics, it's a total game changer. A tiny fiber found at a crime scene can be analyzed to separate out its dyes, which could then be matched to a suspect's clothes. It pulls apart trace evidence and gives detectives crucial clues. So, from a simple spot of ink to the absolute frontiers of science, chromatography is this silent, powerful tool that shows us the true nature of things. The big takeaway here is that nearly everything is a mixture. So the next time you look at a leaf, a pill, or even a glass of juice, just ask yourself, what great chemical race is hiding in there just waiting to be run?